Okay, so the situation that we have now is plotted on the board, and as you can see, these are the 2-point charges, and we want to find what is the electric field due to these point charges. One of them is positive, the other is negative at this point P. Now, before you start any calculation, you can just conceptualize the situation and try to get an idea about how will the electric field of these two charges look like before doing calculations. So the first thing that you show is you show the electric field of each of these point charges, the electric vector, and try to guess how will they add up. So Q1, for example, because it's a positive charge, will contribute a field E1 in this direction. It is along this R. Let me do it better. So this is E1. Why is this so? Because this is a positive charge. This is its corresponding R hat, R1 hat, and so the charge is positive. It will be in the same direction as R1 hat, so at this point it is in this direction. What about Q2? Q2 is a negative charge, and so the point here is this is its corresponding R2 hat. The field here is opposite to R2 hat, so it will be, this will be your E2. So these are the two fields. Now the total field or the resultant field will be E1 vector plus E2 vector. You will add these two vectorially. If it happens, for example, that they are this way, so this is larger, then the field in this case will be pointing somewhere this way. If this were longer, then it will be going down. So it will be in the third quadrant in this case. Here it will be in the first quadrant. So roughly speaking, this will be the field, and it will have X component and Y components. Now, this is how you, this is what you do actually before starting doing any calculations. Try to figure out what will the field look like. So you expect what how the expressions that you will have, how they will come out. Okay. Now the second thing is to do to find analytic expression for these for E1 and E2 and then add them up. Now, as was the case with the single point charge, you remember we said you find first the magnitude of the electric field and then you express it as a vector using any tool that you would like to express a vector. In this example, we will use the unit vectors as our tool to express vectors. And these are, as usual, this is I hat, this is j hat, this is, these are our two unit vectors. So I first want to find E1 and then find E2 and then write them. So what is E1? E1 in this case is K Q1 over R1 square. Okay. Now this is the general expression for it. What I do is I substitute for R1 the variables that are given in the specific geometry that I have. So R1 here is actually square is y square plus a square. So this is K Q1 over a square plus y square. Similarly for E2, I will have K Q2 over R2 square, which is equal K Q2 over B square plus y square. Note the absolute value that I put here because I'm finding magnitudes now. These quantities are positive quantities. These are the magnitudes of the electric field. Now I express this E1 as a vector. Well, to do this, I note that it has X and Y components. And for example, for E1, this is the E1X, and this is the E1Y. This is the x-axis. Now, this angle I call theta, and this angle I call phi. Okay. So if this angle is theta, then so also this angle is theta, And if the angle is phi, this angle is also phi from geometry. Therefore, I express E1 as the x component along I hat, which is E1 cosine theta, and the y component, which is E1 sine theta along y hat. So E1 as a vector, in this case, will be modulus E1 cosine theta along I hat plus modulus E1, sine theta along j hat. Now, from geometry, it's evident that both components are positive, because Ex is along positive I and Ey is along positive j. So what remains is just to substitute in this case, and so this will be k q1 over a square plus y square cosine theta I hat plus k q1 over a square plus y square sine theta j hat. This is E1. Now, in exactly the same manner, I write down E2. E2 will be E2 cosine phi I hat. However, when it comes to the y component of E2, note that it is pointing downwards from here, which is E2 sine phi. It's pointing downwards. So I put this minus sign by hand. So it will be minus E2 sine phi j hat. And now I enumerate it, substituting for E2. This will be k q2 over b square plus y square cosine phi I hat minus k q2 over b square plus y square sine phi j hat. This is your E2. Now I want to find the total E. The total E is just E1 plus E2, and I just add these two vectors component by component. And if I do this, I take just k outside the whole thing, and I will get q1 cosine theta over a square plus y square plus q2 cosine phi over b square plus y square, this whole thing along I hat, plus q1 sine theta, now minus, of course, this is along a square plus y square, minus q2 cosine, sine q2 sine phi along b square plus y square j hat, and k is multiplying the whole thing. So this is the expression for the electric field vector that is the sum of the electric field vectors of these 2 point charges. This is the vector. What remains in real calculations, if you know the values, the numbers, you just substitute in the numerical values and you can find this as a number. Okay? But this is the general procedure. Now, there is a special configuration when Q1 is equal to Q2, which we call a dipole. A dipole is a system consisting of 2 equal and opposite charges that are separated by a distance. And if we further assume that A is equal to B in this case, so that then we will be finding the electric field of a dipole at a line, along a line, which is bisecting the distance between them. Okay? And this is what will be. So if we sketch it here simply, this is plus, so this is plus Q, this is minus Q, this is A, and this is the point P, and this is the distance y. Now, we want to find what is the electric field of this dipole at this point P, which is on the line, vertical line that bisects their distance. Now, we can, of course, evidently use what we have in hand here by saying that in this case Q1 is equal Q2 and is equal Q, which is the magnitude of each of these charges. And also we can say that A is equal to B and theta is equal to phi due to the symmetry. Now, it's straightforward to see now, as we expect, that this expression will give you 0, because when these are equal, they will cancel each other, which is what we expect from symmetry, because when the electric fields of these two charges here, the magnitude of these electric fields will be the same, the angles will be the same, so the y components of the field of Q plus and of the Q plus and Q minus will be equal and opposite, so they will cancel out. You will have only x component, and so these will cancel out, and these two will add up. Okay, so in this case, E, in this case, the meaning of this that E will be twice the one of these expressions in the limit that Q1 equals Q2 and A equals B. So it will be twice K Q cosine theta divided by A square plus Y square along I hat. So this will be the electric field of a dipole. You can do more by noting that in this case, this is y, this is a. So you say that cosine theta is actually equal, and this is theta, which is also this in this case. Cosine theta is equal a over, this is y, and this is y square plus a square to the power square 1/2. Cosine theta is equal a over square root of y square plus a square. So if you substitute this here, you will get A equals 2k q A divided by A square plus y square to the power 3/2 along I hat. So this is the expression, simple expression, compact expression for the electric field of a dipole. Now there is a limit which is usually relevant. That is the limit that y is much greater than a, so that a over y is much less than 1. Now this is an important limit, and if you take this limit, then in this case E, which is 2k qa over, now you take y outside, so it goes like y cube, and you will have 1 plus a square over y square to the power 3/2. This, when a over y is much less than 1, goes to what? You just drop this a square over y square term in comparison to 1, as you can see here, and this becomes, of course I have an I here, this becomes 2k q a over y cube I hat. So when you look at the dipole from a large distance, you see it as like this charge, and it drops like 1 over y cube. Now, dipoles are important objects, especially in chemistry, because molecules, while neutral, sometimes, some molecules, they are polarized. In other words, the positive charge is on one side and the negative charge on other side of the molecule. So it splits. Okay, and this is a natural dipole, quite a tiny dipole, but it's a natural dipole, and many of the properties of the molecules actually are due to these to this dipole structure, and the electric field of such a dipole is important, and especially at large distances, it looks like this.